Hello, everyone. I'm Kevin Cantini, and I will be presenting for UW Formula Motorsports Team 37, my capstone project. And our capstone project is the Forged Carbon Structures Part 2. Our goal was to optimize and validate a short fiber composite material for the T37 vehicle. We wanted to cut mass and unlock geometry that traditional machining couldn't reach. Our target part was the throttle pedal. Specifically, we set out to manufacture a T37 compatible arm, characterize its fatigue life, and establish porosity allowables, as well as document process improvements for future teams. So first, what is forged carbon? Instead of woven sheets of continuous carbon fiber, forged carbon uses short, chopped carbon fibers mixed into a resin to form a moldable paste. That charge gets packed into a closed mold and compression molded. Squeezed under high pressure so that the material flows to fill the cavity, then cures into a solid part. Because the fibers are short and randomly oriented, you give up some peak strength, but you gain a material that flows into complex shapes and eliminates a lot of intricate machining. This is a continuation capstone. Last year's team developed a material system that we're using, including the chopped fiber, the fiber length, and the resin content. Our job is to take that system and push it into a real part and validate it. This is our Gen 1 arm mold. 3D printed in PETG, tougher than PLA, so it survives more molding cycles. It's a 4-part design with a split line that gives us indexing features for drilling the through holes. We designed for manufacturing throughout. A 2-degree draft angle, an M4 bolted flange to locate the halves and seal the split line, chamfers for prying it apart, and a resin content channel, a resin escape channel, and a funnel to keep the full charge contained in the cavity. I'll play the video showing how the mold gets put together. So manufacturing the arms, we had to split the molds into sections to fit our printer's build volume, so there's dovetails on each of the sections. From there, we could weigh and mix the fiber resin charge, pack it into the cavity, and compression mold it under the clamp, consolidate the part, and drive out the excess resin. Here are Generation 1 arms. You can see the problems, voids, and a rough surface finish, concentrated around those sharp corners on the pockets. The fibers couldn't bend around those sharp transitions very easily, so void-prone regions formed exactly where we didn't want them to. Right around those sharp corners, all of those will be load-bearing. That drove our design change to our Generation 2 arms. We had 3 major design changes with these. On the mold, we stiffened the walls, which had been bowing under the clamp load. On the arm, we replaced the rectangular pockets with large radius fillets to remove those sharp features that are creating voids. And in manufacturing, we switched from a release wax that was building up in the corners to proper release agents. These are Gen 2 arms. As a result, we see much cleaner surfaces, much cleaner surface porosity, and just much cleaner arms in general. Then we had to test the arms. We machined an aluminum test fixture to test these arms in the load frame. In straight compression, a potted arm carried 3,827 newtons, and a new arm that was not potted carried 2,226 newtons, well above the expected 1,850 newtons for an aluminum arm with the similar mass. So we're matching or beating aluminum in strength. For fatigue, we defined our cycle count from the worst corners in a year of driving, about 25,000 cycles. A Gen 1 arm passed 30,000 cycles at 1 hertz with a 250 Newton mean and a 250 Newton amplitude. The M3 shock bolt was what actually ended up failing. The conclusions that we made, the Gen 2 arm was 50% lighter than the current aluminum design. It exceeds our expected loads by roughly 10 times and it meets the fatigue life requirement. The design is sufficient. The remaining work is on the process. We'd recommend dropping the release wax for proper agents, keeping every fillet above 3 to 5 millimeters, and evaluating pre-preg as a path to future test panels and better mass savings. We also want more fatigue testing across multiple arms to build statistical confidence so that we have a bell curve of how long the arms last under loading conditions. And our acknowledgements, huge thank you to Dr. Pashith and Dr. Anachi, the shop advisors, Kyle, Eamon, and V, as well as Bill in the mechanical test lab, and then Eli and Sarine. Thank you.